All right. So, good afternoon, everyone. I'm Saket from DataXu. I'm the Senior Principal Data Scientist at DataXu. And what we have today is a very interesting journey. Like last year, we decided to move from Hadoop to Spark. So, we are going to talk about how we went from a research product in Hadoop and Spark to actually implementing it in the product pipeline. And we are going to show a live demo to do that. Can I have the slides, please? Okay. Oh, okay. Cool. So just to give you an overview of what we're going to talk about, we are going to talk about what DataXu does. We're going to talk about why we chose to go with Apache Spark versus other solutions. We're going to give a live demo on how we actually implemented our machine learning system in Apache Spark. And we're also going to talk about how we implemented our analytics platform also in Apache Spark so that everything is on the same software stack. So who is DataXu? How many of you have heard of programmatic marketing so far, just to get a feel of the room? All right, few of you. So DataXu, our mission statement is to make marketing smarter using data science. Our company was spun out of MIT labs, and there was a technology we started using in marketing. What we do is we use machine learning to make smart decisions on what inventory we can buy. We serve more than 1 billion ads every month. The machine learning algorithm we use is very fast. It has to make real-time decisions under 10 milliseconds. And we generate a lot of data, and that's why we're here, of course. So let me talk about what real-time bidding exactly means. And I'm pretty sure all of you in the room have used our software in some way or the other. So whenever you go to any web page on your mobile phone, an app or something, and you see an ad, I'll tell you what exactly happens behind the scenes. So you're a consumer, you go on a website and you see an ad slot. The website then contacts an ad exchange to ask what ad I should show in that ad slot based on a given user. Okay? The exchange basically works in a sort of a eBay sort of a way. There's a second price auction. The exchange will send out a request to everyone in the world saying, okay, who wants to buy this particular ad slot? And you have 50 milliseconds to bid on how much you are willing to pay for this ad slot. Go. So DataXu gets these bid requests from more than 50 exchanges. And what we are doing is we represent the advertisers, the companies who want to show the ads. So we have like thousands of advertisers who have like hundreds of different ads they want to show. So our job is to try to match which advertiser would generate a positive intent from the consumer and try to pick that advertiser. Secondly, as I said, because it's a second price auction, we want to also guess how much we should bid for the particular ad. Like if we bid too high, we would just end up spending all the budget for the advertiser quickly. And if we bid too low, we are going to lose the bids, right? So we are going to bid high on users we think are good. Once we decide what we want to bid, we send it back to the exchange. The exchange gets the responses from all the different players in the market, just like DataXu. And then it selects the person who is bidding the most, and that person gets to show the advertiser's ad in the given ad slot. Now, all this is happening behind the scenes. When you open a web page, you don't see a lag, right, to see the ad. This whole thing is happening in less than 100 milliseconds, out of which we only get 10 milliseconds in our data science engine to make a decision. Now, what we do is we use machine learning to make these decisions. And what we are doing is we are not just showing ads in the wild, but we are also tagging web pages that our advertisers have. Like for example, let's say we are representing an auto company and we are showing ads for a car. Now if you see an ad and then you decide to go to the car's web page and then you want to, let's say, interact with the ad, whatever the advertiser thinks is a positive signal, you go and do that. You also fire a pixel from the advertiser's web page. So whenever we serve an ad, we are also getting positive signals from the advertiser on which person is converting or which person is performing an action or a click, or even when you go on YouTube and you watch the entire video, we get a signal saying that, okay, this person watched the entire video. And our job is to create machine learning models to find users who are going to have a positive intent after seeing an ad. So what we do is we serve ads. Ads are called as impressions in the industry, so I'll refer to them as impressions. We collect a lot of clicks that are generated based on the ads and also collect activities from the advertiser's web page based on those ads. Now, using all this data, we have this huge join that joins all the ads we show and all the positive intent in the market. And we generate a large machine learning data set where for every ad, we know if it was positive or a negative, just like any machine learning algorithm. We feed it to our machine learning training job, and it generates machine learning models for each of the campaigns that we are running. Now, we want to also make sure that the machine learning algorithms we are training are actually able to find some patterns in the positive signal. So when we generate a machine learning model, we evaluate the machine learning model automatically and check if the model meets our requirement. If no, we just use a normal, a prior classifier. But if it does, then we ship the model in the wild. We also have to go through another phase which is called as calibration, where we can't just bid a probability, right? As I said, it's a second price auction. I can't tell the exchange that, okay, I am 80% confident this person is going to convert. So then we have to also check how the market is performing and calibrate our classifiers to actually output a dollar value instead of a probability, which is a very interesting problem in itself. Now, once we do all this thing, we ship all these models to our real-time bidding system, and the real-time bidding system gets thousands of different classification models, and it starts bidding based on that on behalf of all the advertisers we are representing. Again, like just to reiterate, the whole process of the real-time bidding has to happen in 10 milliseconds. And what makes the problem even more difficult is like we are showing ads all across the world, across like hundreds of countries right now. So the main problem is we have to listen to a lot of requests every second from people all over the world who come to the exchanges and try to pick which users should see ads for which advertiser. So right now, DataXu listens to 2.7 million requests every second. And then those 2.7 million requests go through these thousands of classifiers, and we make like thousands of decisions for every request. And we have to do the whole thing in under 10 milliseconds. So we are not only dealing with a large amount of data. Every day we generate 3 petabytes of data, and we train the models based on the 3 petabytes of data. But also we have to somehow take this 3 petabytes of data, train models based on that, and then generate classifiers that would run really quickly and generate decisions. The other important thing is, even though like we're using Spark and everything, the problem is different because we are running across like different countries. So we can't just run a notebook and generate all the models and then have someone ship the models. We have to have an unattended process to do this. So we want a very stable system where we can just deploy the model. Every day it serves ads, collects the data, learns of that, and again creates models and serves ads and keeps on going. And thirdly, as I said, that we are not the only player in the market. We are not the only player who is using machine learning to make decisions. So our machine learning models have to be state of art. If we have a really good machine learning algorithm to find the best users, then only we'll be able to make the best decisions and buy the most efficient media for the advertisers. So we have to adapt quickly and need to have an access to a really good machine learning library in order to train machine learning algorithms. Having said that, I'm going to hand it over to Maximo, who is our data science engineer, and he'll talk about how we actually implemented this system in Spark. Right.
Thank you, Saket. Yes, I'm going to actually go through a demo in Databricks. And even though, of course, as Saket said, we don't actually use notebooks to create models for each daily operation, we definitely use notebooks for it's connecting. We definitely use notebooks to research and find specific improvements that we can make for our models. And suppose a data scientist wants to find an optimal model for a particular scenario, for a particular advertiser, for a particular use case that seems like there's room for improvement. And I'm going to go through the process of how we would get that investigation, that research into production. Let me reset. I have an internet issue over here. It's okay, I have a backup in case. So the internet is gone. Perfect. I do have a notebook here in backup that has already run. You need to trust me. I think that the timestamps are there. But I'll go over the notebook. The first thing we need to do is to collect the data. We're going to split the data for testing. And absolutely. The first thing we would, thank you. The first thing we would do is we would collect the data for testing and training, and we would go and do some data exploration, give a name to this data frame that we use for training. In this case, we call it learning events. Then we'll choose some of the features that we want to pick for our model. This is not real. Of course, it's a very minimal example for this demo. But suppose we want to choose the operating system, the site name, and the user local hour of previous ads or impressions, as Saket mentioned, that we served in order to predict the probability of this ad having a positive action or a positive signal, as Saket was referring to. So look in this case how we use a UDF, a user-defined function, in order to retrieve the operating system given the user agent. We extensively use UDFs for feature engineering. Yeah, we found them very, very useful. And so here's the data, and the label of this data set is what we call an impression or an attribution. An impression means an ad that was shown, but there was no following positive action, whereas an attribution, we don't see right here, but an attribution would show if this ad, once shown, resulted indeed in a positive action, like seeing a video or buying a product in a shop or in an online store. As you can see, we can do some further exploration, identify if the data set is skewed in some form, and you can definitely see that, at least for this particular case, there's a lot of label imbalance, which makes the machine learning problem real hard. So once we did all the exploration, the data scientists would go, okay, I'm going to build a model. I'm going to try to create a pipeline that is able to predict, whether this ad opportunity indeed results in an attribution or just remains at an impression. So in this sample pipeline, it's very simplistic. Obviously, our pipelines are a little bit more complex. It has 6 stages. The first stage is a SQL transformation in which we just select the features we want. We apply the UDFs. We do all the feature engineering right there in the SQL, which is very nice because it's very clear. It's very declarative in nature. And the second stage, or actually it's 3 stages, are the transforming the categorical features into numerical features. For this, we use what we call a top K estimator, which is an extension of Spark's string indexer, but only keeps the most popular nominals. Then we just proceed to assemble the features in a vector. We're using the vector assembler that many of you have probably used, and then use random forest as a Mengle estimator algorithm. Yes? And this is standard Spark. There's nothing specific. Maybe the UDF is the only thing that's specific for us. And we'll go ahead and train this model. And this model is capable of providing predictions given a data set. So if you give an entire data set, this model is able to provide predictions for each row in the model, but you need to submit a whole data set. That's currently the way Spark works. And we can obviously get some predictions for each row of our data set, and you can see here that at the left-hand side we see the features as they originally appeared in the data frame. In the middle we can see the features transform into numerical values. The features column here at the right shows the vectors, and at the last 2 columns we can see the actual predictions and probabilities for each of the classes we're trying to predict. So okay, cool. We can now evaluate our model using standard metrics. For example, in this case, we're using the area under the ROC curve. And you can see that in this case, the area under the ROC curve is 0.66. Might not be a great model, but chances are if we're doing this analysis, it's because it's really hard, and it's better than random. Let's pick this model. I want to ship it to production and run an A/B test, for example, and see if it performs well. So how would we go about getting the standard Spark pipeline defined, there's nothing specific, ship it into production? There is a problem. And many have acknowledged this problem throughout this conference. For example, yesterday at the Clipper presentation, the models that are being produced by Spark are not designed for creating predictions on a row-by-row level. They are designed to create predictions. Given a whole data frame, you can have the prediction. You can fill up that predictions column, but it's not currently easy or possible, out of the box at least, to create predictions given one row. And that's exactly our scenario in real-time bidding, right? We have an incoming bid request, and in a flash of a second, we need to respond with a bid value, right? They don't come in data frames, they come in rows. So that's why we had to create these wrapper classes around Spark that allows us to first mimic the pipeline as we would have defined it in Spark, but using this wrapper classes. That means that every stage, as you can see here, the stages that we created previously are exactly the same stages we inject into our own wrapper pipeline using a builder pattern in this particular case. But it's the same stages, the same Spark stages. Then we proceed to feed the pipeline, feed the data, and what we create here is two things, two different kinds of models. A model that is able to create predictions given an entire data set, much like we saw in the previous example, and a model that is able to create predictions at a row-by-row level, which is the new thing. So this is why we saved two different models over here. So now imagine we save them, they go into S3, we're now on the real-time bidding system, and we want to deserialize those models into memory and see how they perform. Right? We want these models effectively to be fast. And we want these models to perform exactly the same transformations as Spark would have done on an entire data frame, but on a row-by-row level basis. For that, we actually had to implement our own versions of the stages in a way so that they were efficient transformations at bid time, where we have only a few nanoseconds, if you want, to create a prediction. In most cases, though, I have to say that all the transformations that we implemented was just delegating to the right Spark class. So the Spark classes really had the ability to do this, but they didn't come just out of the box. We delegated, in order to implement our own real-time transformation, we delegated into the right Spark class. In some cases, occasionally, we had to implement our own transformation. For example, the SQL transformation that applied a UDF in order to do feature engineering. Exactly the same transformations, including that UDF, need to happen at bid time. So in this particular case, we had to implement our own SQL engine capable of implementing these transformations as UDFs. As you can see in this example, what we did is I loaded 100,000 rows in memory, simulating what would happen in a real-time bidding machine. And I applied the model, the row model, this row model is capable of providing predictions at a row-by-row level, and see how long it took on average to get this prediction. As you can see in the notebook, the average duration of each prediction took 0.14 milliseconds, which is well within the thresholds that we need for making real-time decisions. And with this, I'll present you Sunanda, who's going to talk about where it goes from here in terms of analytics. Oh, just one more note. In terms of the benchmarks, we also benchmarked our own models that we used in the previous system using Hadoop and the new model. And the new model seemed to take as much memory as the previous one. It scaled linearly, and the performance was comparable to one of the very custom models that we used to build. Of course, depending on the scenario, it's different, but it's comparable, it's shippable to production. We can use this out of the box. Thank you, Sunand.
Thanks, Maximo and Saket. So we're going to shift gear a little bit, and what Saket and Maximo were talking about is our core engine, the real-time bidding platform. So DataXu's premise is about making marketing better through data science, and one other element of it is the analytics that we provide to clients. So as you can imagine, there is this real-time bidding engine, and petabytes of data is coming through this, our clients' data. And typically, they have very business-oriented, marketing, industry-oriented questions around this data. For example, let's say we bid for them on a mobile and a display campaign, meaning ads served on a mobile device and ads served on your laptop. We optimized both the campaigns very well, and we figured out that the mobile campaign performed better than the display campaign. So now the client wants to understand why. Can you look into the metadata? Can you tell us why exactly did the mobile campaign perform better? Is the customer segment different? So on and so forth. So these kind of questions, so we need to look back into this big terabytes and petabytes of data that is coming through our system and probably onboard more data from the client and start giving them answers around these kind of business questions. So you can imagine this real-time bidding engine at the core, and there's a layer on top which is the advanced analytics engine, which takes data that comes out of this real-time bidding engine, adds more data into it, does more predictive modeling, analytical modeling, and spits out more data. So we decided to stick with Spark, Apache Spark, for the entire workflow because A, it makes everything standardized. We can all use the same framework. And there are certain other things that makes Apache Spark more suitable for advanced analytics. It makes advanced analytics a reality with its accelerated queries, with its graph processing, streaming analytics. It makes things very easy to do, and it speaks multiple languages. I'm a data scientist, used to be a physicist. I do not want to be brought down by the whole Java Hadoop complexities. It's so much more easy if I can write my Python scripts somewhere and use Spark for it and take the power of Spark's parallelization. So that makes it easy. And our group, it's the Analytics and Innovation group where we have people working in R, Scala, Python, Julia, all kinds of languages. So we needed a framework which was compatible with everybody's expertise because we didn't want everyone to fall into speak the same language. And it makes it easy, as I mentioned. It's so much more easier. I think somebody else was referring to it in this conference. So much more easier to hire people who know SQL or teach them SQL. And once they know that, they can go in and run some Spark queries and do some advanced analytics. And it essentially accelerates the whole data scientist and analyst workflow. It has become so much more easy for us to do some things that would have taken us months of preparing MapReduce jobs and things like that. So this, in summary, is our workflow. So as my colleagues were talking about the real-time bidding engine, the data that is coming out of the machine learning models gets dumped into S3. And depending on the clients and the questions they have, they might be onboarding other offline data or online data, which we also bring into S3. So S3 is our center point. Now, the analytics engine points to S3, and because we are running in Spark, we use Databricks to run most of our R&D work. So that points to the S3 buckets. It picks it up from there nicely. We do our analytics modeling, querying, whatnot in Spark. And then again spit it back out to S3, which can then be picked up by either dashboarding in Databricks itself or further more BI kind of dashboarding. So this framework helps us a lot in keeping things very streamlined and simple. And let me quickly jump to a demo. Can you guys see it or more? So this is a project that is typical for us where teams like the analytics and the machine learning team needs to collaborate a lot. So this is called multitouch attribution. And to give you a very brief introduction to this, the industry, so we as consumers of advertisements and media, look at advertisements on multiple touch points, right? We look at ads on our mobile phone, on our work computer, home computer, TV, so on and so forth. And so far, the industry has been very simplistic in its approach, meaning they want to understand which advertisement got the credit for the final thing you bought on Amazon, right? So typically, they always do what's called last touch attribution, meaning if you saw an ad on your home computer and then you bought something on Amazon, that advertisement gets all the credit. And that's the attribution that Maximo was talking about. But we all know we touch media with different touch points. And that pie chart there is telling you that 75% of consumer journeys are multi-touch consumer journeys. So it would only make sense that you should actually figure out a way to give every single touch point that the consumer makes the right credit in influencing his or her decision to finally make the conversion or the purchase or whatever it is your metric is. So this is a widely studied problem in the industry, and there is a lot of focus now to understand a good model that is not too complex but neither too simplistic, so that people can start understanding insights from this multi-touch attribution. So this project was about creating a multi-touch attribution model, and we were using both the data that was coming out of the real-time bidding engine and clients' data to come up with a model. So this notebook is going to talk about how we went through the R&D phase and how we moved it to dashboarding. So this is a Databricks notebook most of you might be familiar with. We set path names, variable names. We read the data in, and the data is, as you can see, a sample here. It's very messy. It's basically all information that you can get about a consumer journey. So the time the person saw an ad, what device they saw it on, what site they saw the ad on, so on and so forth. There are many, many, many columns there. So we bring it all in from an S3 bucket. We do the usual munging to make it into a somewhat easy to read format. So we've converted it into a nice RDD here. And we basically use graph processing to figure out each consumer, because the consumer does this action on multiple devices. There should be a way for us to connect all these journeys into one single consumer journey. So we do all that, and that's where the power of Spark comes in, because this is impossible to do it on a regular Python script. So then we look at what's called conversion trails and non-conversion trails. Conversion trails being consumer journeys that finally led to a positive signal, wherein you purchased something or did something that is that shows that you actually were positively influenced by marketing. Non-conversion meaning the advertisement really didn't have any effect on you. So as data scientists and analysts, we want to look at quick descriptive stats. So this is the typical data universe that Maximo was pointing out too, which is you have a lot of negative signal in the data. So this is non-conversion versus conversion trails. You always have a lot of non-conversion trails. You have like 1% of conversion. Then you pare down the data to the features that are more important to you. You write functions, you create a whole pipeline. There is a separate notebook where we have all these functions. I've given a sampling of some of the functions here. And so we now are reduced to just 3 columns here: spend, channel, and whether it was an impression or a conversion, which Saket explained earlier. We dump it into a data frame so that we can do further typical standard analytics with it, query it, look at the bar graphs, understand your data, which channel, advertising channel is heavily invested in. So this is a sum of spend across display and mobile. So this is a very display-heavy channel, so which is important to address in your model. And then we finally run the model, and then we start getting out results. For example, this model took 7 minutes, you can see there. And we start getting out actions and attribute it to each of the channels. So we are doing this multi-touch at the channel level, meaning figuring out how many actions or conversions were attributed to mobile versus display. And we also do it to last touch, because the whole point of going the multi-touch way is that there is some change from last touch to multi-touch. So then we look at the change. Okay, so mobile went down actually in this model, and display gained more actions. So okay, this is interesting. Maybe not the perfect model. So then we look at more granular level. Can we gain insights at the site level? So can I attribute at the site level every single action that happens? So you can do the same with this notebook. It becomes so easy because now you have the separate pipeline which has all the model stored in it. You just increase the granularity of your data set, apply the model, do the usual analytics with it, and keep dumping out all the outputs that you get from the model to S3 buckets. And you rerun the model at lower aggregation and get the results, dump it out to S3. And now the nice thing is you can actually, in Databricks, create a dashboard here to sort of check how things look. And I think because of the internet connectivity, things didn't populate here. But essentially, all the charts and everything that you're doing in your R&D phase can all be collected into this dashboard. So as a data scientist who needs to then go on and make more prettier BI level dashboarding, this is very useful for me because I can start looking at, okay, this campaign was good, this model was good, these are the things that I want to actually be populated in my dashboard. So it's all available in S3 anyway because my script was dumping everything to S3. And then, boom, my real-time dashboard just points to that S3 bucket, refreshes as soon as I'm done with my R&D pipeline. So this was an example where we basically heavily use Apache Spark and Databricks to collaborate, build analytics dashboarding, and the next vision is basically Spark streaming, do real-time analytics, right? So, and this also makes it very easy to collaborate with other teams. For example, now the results from my model is in S3. It can be picked up by Maximo and Saket's team, who can now use that insight to actually do active bidding, right? So what was analytics becomes active analytics because that team can now act on it and bid based on this information. So this is, in short, our story about how we use Apache Spark to go from R&D to R&D phase and to product pipeline. And that's pretty much it. And I would like to thank you for your attention. And also note that we are hiring data scientists, data science engineers, full-time employees, interns. So please reach out to one of us, and we'll be happy to tell you more. Thank you. Any questions?
Yes. So the models that Spark provides out of the box, and we reuse a lot of what the infrastructure of Sparks is indeed like thread safe and is fast, but in nature. So we can definitely use Spark's models live at that speed. So they're good enough, And in terms of how we ship them to production is we store them in S3. We have the synchronizing mechanism with the real-time system that loads models every so often, swaps the old one and replaces a new one. Like Saket was mentioning, we do have an automatic system that is training, replacing, selecting models and swapping models in and out as the market trends indicate so.
Yeah, sure. I mean, so we do a lot of things. Like first is sampling negatives is one of the main things we should do, especially in terms of evaluation phase, like never evaluate on like a very unskewed data set. The other things we do is like we also like when we see a positive signal, we try to get pseudo positive signals. So even though our positives are less, we try to get like people who are halfway there or like stuff like that. So we try to get as much signal from the market as possible. And we have a lot of different tricks that we use to do it.